NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn a practical algorithm for solving inequalities with the floor function, also called the bracket function. Then we will apply the rules to a short example. First, here is our reference example statement, shown exactly as a bold, orange formula. We'll come back to it after we build the rulebook. Rule 1. Strict less than with an integer bound. If the floor of x is less than n, then x itself must be less than n. Rule 2. Less than or equal to. If the floor of x is at most n, then x is strictly less than n plus 1. Rule 3. Strictly greater than. If the floor of x is greater than n, then x is at least n plus 1. Rule 4. Greater than or equal to. If the floor of x is at least n, then x starts at n. Rule 5. Handle coefficients in front of the floor. Isolate the floor first, then use the previous rules. If the threshold is not an integer, round up with the ceiling. Rule 6. Compound interval for the floor. Combine the lower bound and the upper bound results. Quick challenge. Predict the next step before it appears. Suppose 3 is less than or equal to the floor of x, which is less than or equal to 5. What interval for x do we get? We'll apply the compound rule. First, from floor of x greater than or equal to 3, we get x greater than or equal to 3. Next, from floor of x less than or equal to 5, we get x strictly less than 6. Finally, intersect the two to obtain the solution interval. One more mini example with a coefficient, 2 times the floor of x, at least 7. Isolate the floor, then apply the ceiling. We find x at least 4. Let's summarize the key ideas, then you can try a few on your own. Remember, strict versus non-strict inequalities shift the bound by 1 when moving from the floor to x. Compound ranges intersect lower and upper results. Next, explore the fractional part function for deeper insight. We will solve the inequality x plus floor of x is greater than 0, following the exact step-by-step algorithm shown in your image. First, show the label example, then the problem in orange. Step 1. State the initial inequality exactly as given. We show a rule box titled Given Inequality, then the step title, and the inequality x plus floor of x greater than 0. Step 2. Isolate the floor term by subtracting x from both sides. We show the subtraction property rule box, then the step title, and the transformed inequality, floor of x greater than negative x. We highlight negative x in orange. Step 3. Determine the condition on x. We use the floor function case rule. If x is in the interval from n to n plus 1, the floor is n. Then, the step title. We will quickly test sample values and show a number line to see which side works. 4x equals negative 0.5. The floor is negative 1, sum is negative 1.5, not greater than 0. 4x equals 0. The sum is 0, not greater than 0. 4x equals 0.2. The sum is 0.2, greater than 0. Therefore, x must be greater than 0. Step 4. State the solution set in interval notation. We show the interval notation rule box, then the step title, and finally the domain d equals 0 to infinity, open at 0. We will solve the inequality, floor of x minus absolute x greater than or equal to 0, exactly following the algorithm shown. First, we show the problem as an example. Then we write the inequality in bold orange. Step 1. Isolate the floor function using the addition property of inequality. The rule says a minus b greater or equal to 0 implies a greater or equal to b. Now apply it to our inequality. We get floor of x is greater or equal to absolute x. Quick challenge. Is the floor of x ever greater than x itself? Step 2. Split into cases using the absolute value definition. The rule says absolute x equals x if x is greater or equal to 0, and equals negative x if x is less than 0. Now, write the two cases for our inequality floor of x greater or equal absolute x. Case 1, floor of x greater or equal x, for x greater or equal 0. Case 2, floor of x greater or equal negative x, for x less than 0. Step 3, analyze the intersection of conditions. Use the integer property. Floor of x equals x if, and only if x is an integer. For x greater or equal 0. Since floor of x is always less or equal to x, floor of x greater or equal x forces equality. So floor of x equals x, and x is an integer. For x less than 0, floor of x is negative, and negative x is positive. So floor of x greater or equal negative x never holds. Therefore, we keep the conditions floor of x equals x and x greater or equals 0. Step 4. List the solution set. Since floor of x equals x means x is an integer, and x is greater or equals 0, we get all non-negative integers. D equals the set 0, 1, 2, 3, and so on. In this guided example, we will follow a precise step-by-step structure with rule boxes, highlights, and checks. We begin by clearly stating the example. Here is the problem statement in bold orange math. Rule: substitution. We introduce a simple substitution to turn the expression into a standard quadratic form. Step 1. Substitute the floor function. We write 3 times floor of x minus floor of x squared greater than or equal to 0, and floor of x equals t. Predict why substitution helps here. Rule: quadratic form. We aim to recognize and solve a quadratic inequality. Step 2. Rewrite the inequality. It becomes bold. 3t minus t squared, highlighted in orange, greater than or equal to 0. We now see a downward opening parabola because the t squared coefficient is negative. Rule: interval of roots. Factor and find where the quadratic is non-negative. Step 3. Solve for t. We write t times 3 minus t greater than or equal to 0, which implies bold, highlighted in orange, 0 less than or equal to t less than or equal to 3. Rule: back substitution. Replace t by floor of x. Step 4. Return to the floor function. We conclude bold, 0 less than or equal to highlighted floor of x less than or equal to 3. Rule: floor definition. For any integer n is less than or equal to floor of x, less than n plus 1. Step 5. Solve for x. From 0 less than or equal to floor of x less than or equal to 3, we get bold, highlighted 0, less than or equal to x less than 4. Step 6. State the domain. We conclude bold, d equals the interval from 0 to 4. Nicely done. Example. Our goal is to solve the inequality. Floor of x cubed minus floor of x is greater than or equal to 0, step by step, and visualize each step clearly. We begin by substitution. Use t for the floor of x. Then the inequality becomes t cubed minus t is greater than or equal to 0. Next, factor the expression. We use a cubed minus equals a times a squared minus 1. Applying that gives t times parenthesis t squared minus 1 right parenthesis greater than or equal to 0. Quick challenge. Can you name the roots? Now analyze intervals. For the sign of t times t minus 1 times t plus 1, we check the roots negative 1, 0, and 1. Highlight where the product is non-negative. The solution for t is the closed interval from negative 1 to 0, together with 1 to infinity. We include endpoints because the inequality allows equality. Rewrite as a system of inequalities. We have negative 1 less than or equal to t less than or equal to 0, or t greater than or equal to 1. Translate back to x using the floor definition. If n is less than or equal to the floor of x, and the floor of x is less than or equal to m, then n is less than or equal to x, and x is strictly less than m plus 1. From negative 1 less than or equal to the floor of x less than or equal to 0, we get negative 1 less than or equal to x, and x is less than 1. From the floor of x greater than or equal to 1, we get x greater than or equal to 1. Combining gives x greater than or equal to negative 1. Summary. We substituted t equals floor of x, factored the expression, used interval analysis to find where the product is non-negative, then translated the inequalities back to x using the floor function definition, concluding that x is greater than or equal to negative 1. We will solve the inequality. Negative 3 times the floor of x is greater than or equal to 15, following the exact 4-step algorithm. First, let's display the example and the problem itself. Step 1. Isolate the greatest integer expression. We will divide both sides by negative 3. When we divide an inequality by a negative number, the inequality sign flips. Step 1. Isolate the greatest integer expression. This gives the floor of x is less than or equal to 15 over negative 3. Step 2. Simplify the fraction. We use basic arithmetic to simplify 15 divided by negative 3. Step 2. Simplify the fraction. So we get the floor of x is less than or equal to negative 5. Step 3. Solve for x using the floor function property. If the floor of x is less than or equal to n, then x is strictly less than n plus 1. Step 3. Solve for x. Here n is negative 5, so x is less than negative 4. Step 4. Write the final solution set. Step 4. Write the final solution set. The domain is all real numbers less than negative 4, which we write as open parenthesis negative infinity comma negative 4 close parenthesis. Great work following the algorithm precisely. Summary. We isolated the floor expression, simplified, used the floor inequality rule, and wrote the solution set. Practice problem. Solve negative 2 times the floor of x greater than 10. Next topic, equations with the greatest integer function. We will follow the exact step-by-step algorithm to solve the inequality 2 times the floor of x is greater than or equal to negative 7. First, we display the example and the problem statement. Step 1. Isolate the floor function. We use the division property to divide both sides by 2, which is positive, so the inequality direction does not change. This gives the greatest integer of x is greater than or equal to negative 7 over 2, which is negative 3.5, not an integer. Step 2. Apply the floor inequality rule. When a non-integer bound k appears, we move to the next integer at or above k, which is the ceiling of k, equivalently the floor of k plus 1. Therefore, x is greater than or equal to the floor of negative 7 over 2 plus 1. Step 3. Simplify the expression. The floor of negative 3.5 is negative 4. So x is greater than or equal to negative 4 plus 1, which is negative 3. Great work! To visualize the solution, here is a number line with a closed dot at negative 3 and a green ray to the right representing all x greater than or equal to negative 3. Step 4. Define the solution set. The solution set includes all real numbers greater than or equal to negative 3. In interval notation, we write d equals bracket negative 3 comma positive infinity parenthesis. Example. Solve the inequality involving the floor function, bracket x end bracket squared, minus 5 times bracket x end bracket, minus 6, is less than 0. Step 1. Substitution. We let y equal the floor of x, so that the inequality becomes a standard quadratic. That gives y squared minus 5y minus 6 less than 0. Step 2. Factor the quadratic. We look for two numbers that multiply to negative 6 and add to negative 5. Those are plus 1 and minus 6. So the factorization is open parenthesis y plus 1 close times open parenthesis y minus 6 close less than 0. Step 3. Solve for y. For a factored quadratic less than 0, y must lie strictly between the roots. The roots here are negative 1 and 6. Therefore, negative 1 is less than y, and y is less than 6. Step 4. Back substitution. Replace y with the floor of x. We get negative 1 less than floor of x, less than 6. Step 5. Interpret the floor bounds. By definition of the floor function, floor of x greater than negative 1 means floor of x is at least 0, so x is at least 0. And floor of x less than 6 means x is strictly less than 6. That gives two sets x in the interval from 0 to infinity and x in the interval from negative infinity to 6. Let's visualize these on a number line and then take their intersection. Step 6. Intersect the two sets. The intersection of 0 to infinity and negative infinity to 6 is 0 to 6, including 0 but excluding 6. So the final solution set is x in bracket 0, 6 parenthesis. Let's highlight that on the number line. Final answer x is in the interval 0 to 6, including 0, excluding 6. Quick summary. We substituted y equals floor of x, factored and quick summary. We substituted y equals floor of x, factored and solved the quadratic inequality, back substituted to get negative 1 less than the floor of x less than 6, interpreted the floor bounds, as x in 0 to infinity and x less than 6, and intersected to obtain the final solution, 0 to 6. Example: we will solve the inequality open bracket x close bracket squared minus 7 open bracket x close bracket plus 6 is greater than or equal to 0. We'll follow 4 clear steps: substitution, factoring, solving for the integer floor, and then writing the final solution set. Step 1. Substitution. We introduce a helper variable to stand for the floor of x. Let open bracket x close bracket equal y. Then the inequality becomes y squared minus 7y plus 6 is greater than or equal to 0. Step 2. Factoring. We factor the quadratic. We need two numbers that multiply to 6 and add to -7. They are -1 and -6. So it factors as left parenthesis y minus 1 right parenthesis times left parenthesis y minus 6 right parenthesis is greater than or equal to 0. Step 3. Solve and back substitute. For a product to be non-negative, y must be less than or equal to 1 or greater than or equal to 6. Next, we translate each y condition back to x using floor function properties. If the floor of x is less than or equal to n, then x is strictly less than n plus 1. If the floor of x is greater than or equal to n, then x is at least n. So y less than or equal to 1 gives x less than 2, and y greater than or equal to 6 gives x at least 6. Let's visualize the solution on a number line. Step 4. The final solution set is the union of the two intervals. -infinity to 2, union with 6 to infinity. Quick summary. We replaced the floor with a helper variable y, factored the quadratic, used floor function properties to translate y ranges back to x, and wrote the solution set as a union of intervals. Try this next. Solve open bracket x close bracket squared minus 5 open bracket x close bracket plus 4 is less than 0. Squared minus 5 open bracket x close bracket plus 4 is less than 0. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.